thank you, Stefano, for the invitation. Well, welcome all of you. Special thanks for the people that are going to give the mini courses. I hope that the note takers, the groups are finding themselves. There are some of the organizers that will contact the people that are volunteer to take the notes of the mini courses. Just a quick note: there are 2 schedules. I hope that doesn't give too much confusion. This is the one of the ICTP, and then the other web page which will have some additional material. Hopefully, it also has the schedule. But yeah, you received this already. There's one remark about the lightning talks, because the people from the technical support, they leave by 5. So if you have a lightning talk in the afternoon, so you should come at 3 before the afternoon session, just to put your PDF in case you are using a presentation. Okay, I think this is all. Anything else? So welcome again in name of all the organizers. The first talk we start with Amie Wilkinson. Okay.
Okay. Sorry, I'm getting over a cold. Can everybody hear me?
Yes.
Okay, great. Well, thank you so much, Katrine and organizers, for this. Should I start the talk, or you look like you're going to say more?
I was waiting to announce you. Okay, first.
Oh, you were going to announce me. I'm sorry. I thought you did just announce me. No.
Why not?
Sorry.
I'm here. So the first speaker is Amie Wilkinson from Chicago, and she's speaking about the dynamics of expanding foliations.
Thank you. Thank you again, Katrine. And thank you, the organizers. This is a very special conference to me, and I'm actually delighted to see so many people here. This conference, I think, traces back its origins to a conference that Keith Burns and I organized at Northwestern University in 2001, which was a conference on partial hyperbolicity. And then over the years, the venues have changed and the organizers have changed. I'm no longer an organizer, but was for many years. And the name changed at some point as well. But it started out quite small. I recognize several people in this audience who were actually there in 2001 and have regularly been here since then. So for the very first talk, I think it would be kind to give you kind of a nice overview of the themes of the conference or the history of the conference. But instead, there was a request that I give a technical talk about some work myself and Sylvain Corvisier and Arthur Avila, who unfortunately couldn't make it. So I've also prepared too many slides. So I know we're off to a good start, but I've set myself a timer, or I'm about to set myself a timer so I don't go horribly over. Okay, so let's start. Okay. So this part of the talk is a somewhat general introduction. I stole this shamelessly from a talk that Sylvain once gave on the subject because I thought it was very nice. So the subject of this talk is really partially hyperbolic dynamics, which was, in fact, the theme of the very first conference in this series. So it's a bit historical in some sense, or at least it refers back. But one could sort of fit the discussion in a larger framework, which many people recently have been working on. And I will mention some of them, but I'm sure I will miss others. So the focus of this talk is our expanding foliations. Learning this clicker. Okay, so throughout the talk, M is a closed Riemannian manifold. That means compact and without boundary. And F is a diffeomorphism. I will specify the regularity when it's appropriate. And F is a foliation of M. And in general, F will be a foliation that is invariant under the diffeomorphism F. Okay, it does not work from this distance. It's a little bit of a learning curve. Oh, it's the middle?
Yes, it's the big. No, it's this one.
No. It's this. It's just not. There we go. Okay, I just have to maybe point it or something. Okay, here we go. Okay, good. So there you got the whole. I saved some time there. Here's the definition of what it means for a foliation to be expanding. So I in fact forgot to say that F should also be invariant under little f. Leaves of F are taken to leaves of F. We say it's expanding if there's a Riemannian metric on the manifold such that that leaves, tangent vectors to leaves of the foliation are expanded by some factor greater than 1 under the derivative. So what you would expect the definition to be. Yeah. For some reason, I like, this is faster, probably. Okay. So there's a picture of an expanding foliation for a family of diffeomorphisms that belong to the same class, okay? The same isotopy class of 1112, the famous cat map. And there is an example of a picture of some leaves of that expanding foliation. And over here is a foliation. It's a Rabe foliation of the 2 torus with 2 compact leaves indicated in blue. And to make sure you're paying attention, why is that not the expanding foliation for any diffeomorphism? Raise hand. Yes. That's exactly. So this foliation has a compact leaf, this circle, and none of the other leaves are compact. And so this leaf would have to be preserved by a diffeomorphism preserving the foliation, but the expanding condition is incompatible with it being invariant. Okay, so this is just make sure you're, okay, not expanding. Okay, just to illustrate the concept. Now, just as one studies the dynamics of maps, one can study, and this is classically studied, the dynamics of foliations. There's several ways to do this, but the kind of most basic one is to replace the notion of orbit with the notion of leaf. And in that way, one can talk about things like minimality, transitivity, and so on. So the topological dynamics of any foliation, not just expanding foliations, has a basic building block that is kind of the indecomposable minimum topological object, and that's what we call an F lamination, which is a union of leaves of F that is compact. And one can ask that such a lamination be invariant under little f. That's an extra kind of assumption. But an F lamination is just a union of leaves. And then I said minimal, I didn't mean to. Just as any continuous map has minimal sets, any any foliation or lamination, in fact, has minimal sublaminations, ones that contain no smaller ones. And so the kind of most basic classification problem in this setting is to classify the F laminations, and in particular, what are the minimal F sublaminations. And if there's only one, So we have a foliation or lamination, and every leaf is dense, we say that F is minimal because the foliation or lamination is the unique minimal sublamination. So we are interested in this property of minimality of these foliations, and I will explain why in a couple slides. And then one can also consider the ergodic theory of foliations. And again, there are many, many ways that one could talk about ergodic theory of foliations. And this is only one of them, and I would say it gives preference to certain kinds of measures, the kinds of measures that arise empirically, and they're the kinds of measures that one sees in Sinai-Ruelle physical measures, for example. And these are what we call the F states. So an F state, given a foliation, expanding foliation, let's say, an F state is a probability measure on M, invariant now under little f. So we introduce little f again, with absolutely continuous disintegration on leaves. So locally, if you disintegrate this measure, you see something that looks like volume along the leaves. And transversely, it might be something else. And problem 2 in this theme is to classify the F states. When is there a unique ergodic F state, or unique F state, which would automatically be ergodic? And when are the ergodic F states, this is related to the previous question that I didn't mention, but what can we say about the support of the ergodic F states? That goes back to the topological question, and one could further ask, are the ergodic F states supported on compact submanifolds, smooth compact submanifolds? So I said I would give some justification for why one would be interested in the dynamics of expanding foliations, and a main one is that the dynamics of F, of expanding foliation, is closely related to the dynamics of little f. So in particular, if little f is minimal, every leaf is dense, then for example, we have that little f is mixing. So this is not hard to see. Yeah? Oh, it's the batteries. Okay, well then I'll use chalk for a minute while this is happening, if I can find some chalk. So, so what does mixing mean? It means that if I have two sets of almost the same color, U and V, then there's some pre-image of one of them, say f to the minus n of U, that intersects V and continues to intersect V under all iterations. So ignoring, you can sort of fill in the details of the proof, but if I have a set U, and I have, or let's think over here, sorry, of V, if I have an open set V, non-empty, then I can find a leaf of F that's, a piece of a leaf of F that's contained inside of V, and then via iteration, I stay within F, and this gets longer and longer because it's expanded. And eventually, I get very long. And when you have a minimal foliation of a compact manifold, once it's long enough, it's forced to intersect. One has to be a little careful, but once it's long enough, it's forced to intersect another open set. So you can make sense of this and turn this into a proof. So minimality implies this strong property of topological mixing. So that's one example. And another is if you have a unique F state, then it has to be physical, meaning that with full volume basin. So this connects the dynamics of F to the dynamics of curly F in a very strong way. So indeed, for almost every X in M, if I take any continuous function, we have to have convergence of the forward ergodic average to the integral of F with respect to this unique F state. Okay? So I'm going to mention this again later, but in the very first Beyond conference, we had a lecturer. So we started this whole idea that we wanted to have lectures and a few talks, and then time for conversations was very important. And Dima Dolgopiat, who's right here, gave a lecture series on F states, which you can still find the notes for this online, and people still read these and are influenced by them, 25 years later. It's kind of insane. But anyway, so this is something he taught us years ago, and this is working much better. Okay, so just recalling the definition of expanding. Okay, not that much better. Okay, a little bit better. So I wanted to give some, I hope, well-known examples to most people in this room, and that is the unstable foliations of an Anosov diffeomorphism. So in an Anosov diffeomorphism of M, you have a DF invariant splitting of the unit tangent the tangent bundle into expanded and contracted bundles, and there are foliations tangent to both of these. And the unstable foliation is an example of an expanded foliation for that particular diffeomorphism. And the stable foliation is expanded by DF inverse. Is an expanding foliation for F inverse. So for example, this perturbation I showed you a picture of last time, the perturbation of the, last time, a few slides ago, of the CAB map. So that foliation I showed you was an expanding foliation for this Anosov diffeomorphism. So that's the first example, and another class of examples is the unstable foliations of a partially hyperbolic diffeomorphism. And in this case, the tangent bundle to M splits invariantly into a direct sum of 3 bundles in a non-trivial way. These aren't really pointing very well. This is expanded direction, and this over here is a contracted direction. And in the middle, this is the direction, the center direction that's dominated by the other two. And one is always guaranteed, as in the Anosov case, to have foliations tangent to the unstable and the stable. And just as in the other situation with the Anosovs, these are invariant expanded foliations for F and F inverse, respectively. Okay, so now no one has to define partially hyperbolic for the rest of this. No, okay, maybe you probably should do a better job than that. Okay, so just looking at these examples, what are the dynamics of the foliations? Well, for an Anosov diffeomorphism, if it's transitive, and this is sort of an annoying but necessary at this point assumption, if you have an Anosov diffeomorphism that's transitive, then the unstable foliation is always minimal. And this is a classic result. And in particular, I told you that minimality implies mixing, so you could say this minimality implies mixing, which is true. Of course, you can just prove mixing by other means as well. So that's reminding you what it looks like. And in fact, as going toward our second problem, there is a unique WU state, or sometimes these are called U-Gibbs states or Gibbs states. And this particular unique state is the well-known Sinai-Ruelle-Bowen measure, the SRB measures, which have this property that the measure is forward generic with respect to volume, in the sense that I mentioned before. So what about partially hyperbolic diffeomorphisms? They're very close to Anosov. Well, as the examples will show, the unstable foliation is not always minimal. And in fact, in general, we don't, even with the assumption of transitivity, it might not be minimal. So it's not the same situation as with Anosovs. And while these WU states or UU-Gibbs states in other equivalent language, they always exist. But you may have many UU-Gibbs states. They might not be unique. The one nice thing about these measures, though, is that the U-Gibbs states, the measures that are absolutely continuous along unstables, is that they form a compact set in the weak star topology. And so, and they behave well under perturbations. So, so they're very, they're a good family of measures to work with, but they might not be unique. Let's give an example now. Here's a partially hyperbolic diffeomorphism of the 3 torus. It's the product of a cat map on the 2 torus and the identity in the circle. This is my favorite pathological example of a quasi-pathological example of a partially hyperbolic diffeomorphism. You can think of the 3 torus as a circle bundle over the 2 torus. And here the dynamics are just 2, 1, 1, 1 on the base. So there we think of it as a bundle. And on the fiber, they're just the identity. And this is not at all topologically transitive. We could change it to be topologically transitive and get a similar condition by replacing this identity, say, with rotation, a rotation by some irrational amount on the circle. That would be transitive. But either way, the stable and the unstable directions are tangent to, there's a horizontal foliation, and the stable and unstable directions, now this is, are tangent to this horizontal direction. They're just the stable and unstable for this factor. And so the unstable foliation in particular is not dense, okay? So in this example, if you take a point and you follow its strong unstable manifold, you get, and you take the closure, you get a torus. So it's a UU lamination or an FU lamination that is not the whole thing. And of course, I get one for every point on the circle, even in the case where the second factor is an irrational rotation. So this is really sort of a fact, this is a consequence of the fact that this is a product. But in this special case, it has this a sort of nice property I want to note, that the closure of any leaf, while not being everything, is actually a smooth submanifold. It's a torus. And moreover, if I look at the unstable and the stable for this diffeomorphism, they are jointly integrable, and they give you this torus. So this is a theme that I will return to later. But this is a highly non-generic example. If I do an arbitrarily small generic perturbation of this, these tori will disappear, and I will go back to the situation where it's possible that the submanifold, that the closure is everything. I'm not making any claims at this point, but this can't happen at least. Another example So this specific example that I'm going to give appeared in a paper by Gogolyev and Kolmogorov and Maimov like 5 to 10 years ago. It was an undergraduate project with Andre. And they considered the following linear map on the 3 torus, which looks almost like the other one, but is very different. It has this linear map on the 3 torus has 3 eigenvalues. One of them is greater than 1, and strongly so. The other is real, but less than this one. And then there's one less than 1. So it has a 2-dimensional unstable direction and a 1-dimensional stable direction. And any Anosov diffeomorphism, linear Anosov diffeomorphism of the 3 torus is going to have 3 real eigenvalues that either split this way or in the inverse the other way. Oh, I'm pressing the pointer. It's not only Anosov, but it's also a partially hyperbolic diffeomorphism. So it's Anosov, and you can also view it as partially hyperbolic, where you view the center as being tangent to this weaker unstable. Okay, so here's, there's a partially hyperbolic splitting of this form, where the unstable, or the center, is actually expanded. Now, for this case, this linear map, this is just a schematic. But basically, every single foliation you can think of has dense leaves, is minimal in the torus, okay? So that's the situation. It's for kind of linear algebra, algebraic reasons that this is the case. As you can imagine, this form of minimality might also be very sensitive to perturbations, just as the integrable, the closure of a leaf being a torus and the stable and the unstable being jointly integrable is also very sensitive, and you would expect it to be destroyed. So what happens if we perturb these 2 examples in particular? Just a smooth perturbation. So what do I mean? I perturb the diffeomorphism F, which will perturb the foliations in a continuous way. Now we can ask, what is the behavior of the new unstable or strong unstable? So this question, in a more general context, but specifically in example 1, was treated quite a while ago by 3 guys who were at the very first Beyond conference in 2001. And I will say more about what they did, but they discussed this example and what happens when you perturb it and what happens to similar examples. So does that 2-dimensional torus persist as the closure of a leaf? Okay. And there was subsequent generalization, removing a few hypotheses. The hypotheses were actually true for perturbations. But more generally, this was studied by Federico and Hanna Rodriguez-Hertz and Raul Ores. Okay. And then example 2, as I mentioned, was discussed in this experimental paper of Gogolyev, Maimon, and Kolmogorov. I did that out of alphabetical order for some reason. More recently, and subsequently, there's been more work on these examples showing, illuminating more properties of what happens to this unstable foliation, the strong unstable in your perturbation. Okay, so just a word about what Bonatti, Diaz, and Ures did. So they considered exactly this question of minimality for strong stable and strong unstable foliations of a partially hyperbolic diffeomorphism. They added an assumption. So transitivity, I just told you, of F is not enough to get minimality. So they added this property of robust transitivity, so transitivity that is preserved under perturbation. Strongly partially hyperbolic, well, forget about strongly. We don't worry too much about that these days. But they're talking about the same thing, basically. And they were able to address this question using magic horseshoes, or what they called blenders. Blenders were discovered by Bonatti and Diaz earlier, or maybe not discovered, but utilized in a novel and creative way to establish robust transitivity that's stable under perturbation. And they also use this to establish, so you can produce these things once you have, in this particular setting, you can produce these things when you have a heterodimensional cycle, which you can arrange pretty easily. But so anyway, they assume that you are robustly transitive and you have a blender like this. Then what they showed is that either, so think of the first example, I'm perturbing Anosov times the identity. And what they proved is that either the unstable manifold is transitive, either the unstable foliation is minimal, or the stable foliation is minimal. So it's in a C1 open and dense kind of way. Okay, so this was kind of this first example of smooth, robustly minimal foliations, although you sort of don't know which was stable and which was robustly minimal. There's a reason for that, which I might mention later. The second example, well, in fact, the result of Bonatti, Diaz, and Ures also applies to the second example. Remember, we have a one-dimensional stable, a strong unstable, and a weak unstable, which is the center. It applied in that case as well, but it's kind of a trivial conclusion because it's Anosov, and we already know that the stable is minimal. Okay, so, but as I mentioned before, this was experimentally investigated in this paper, this particular example. And they defined, in fact, two classes of perturbations of that initial linear map I described. First was conservative, and the second was dissipative. So looking at the conservative maps, they did a careful simulation. Oops, I turned it off. I knew that was going to happen. Okay. They did two kinds of simulations. The first, basically, you have this strong unstable after perturbation, and you take a cross-section to it in the center stable direction, and they traced the trajectory of this unstable leaf, the strong unstable leaf, through this cross-section. And they saw that in the conservative case, this leaf distributes very much like you would imagine a randomly chosen orbit under, it distributes very much like Lebesgue measure, is what I want to say. So it supports the idea that the measure that's supported on this leaf, the measure that's absolutely continuous, any measure absolutely continuous on this leaf, is going to transversely look like Lebesgue measure and therefore be volume. And since this is a volume-preserving diffeomorphism, this says there's a unique. They also did a simulation with a dissipative example, and similarly, they obtained a picture that looks very much, this is the picture of the SRB measure, how it would be distributed transversely, and this is the picture for the perturbation for the strong unstable. So strong experimental evidence, and that's not a straightforward thing if you think about it to simulate. So it was an interesting experiment as well. And so they made a couple conjectures, basically saying that this foliation should be minimal. Well, actually, they were very cautious in their conjectures. But essentially, they conjectured minimality. Actually, they conjectured something weaker should hold for the generic perturbation, and that there should be a unique U-Gibbs measure. In fact, I guess the second conjecture actually implies a strengthening of the first conjecture, because it would imply minimality as well. So just pay attention to the second conjecture. Okay. And so I want to say something about this conjecture, this example, and then more about sort of general partially hyperbolic diffeomorphisms. So the class of diffeomorphisms I will restrict to at this beginning is the following C1 open class. So we look at any Anosov diffeomorphism, any dimension, where the unstable direction splits as a strong unstable and a center. I have a feeling that would happen. Okay. Jeez. Voicemail. Okay. It's because I wanted to make sure that the alarm went off when I okay. When I okay. Okay, I have 22 minutes, so this is absurd, the amount I planned. Okay, so this is the class I want to consider. And so there it is. So it's like the second example, but in general. And our first theorem says, okay, let's look at this class, but let's assume the center is one-dimensional. And we don't know what to do when the center is higher dimensional, though we have some ideas, but it's really important that it be one-dimensional for these results. So the first is an open and dense set, sort of the nicest type. It's a topological result. And it says that among these smooth diffeomorphisms with 1D center, there is an open and dense set where the strong unstable is minimal. So generically, this is the case in a very strong way. It's the strongest notion of openness and the strongest possible notion of density. Our second result is a joint work with Eskin and Potrier and Jiwan Zhang as well. And this goes back very specifically to the second example. So we consider, for example, perturbations of that linear map considered in the experiments. But any Anosov diffeomorphism with 1D expanding center, there are only, well, first of all, the unstable is always minimal. It's not just generic, it actually always holds. And there are two possibilities. Either, remember I mentioned this before, if the stable and unstable could be jointly integrable. That's a possibility. We don't know what to do in that case, but we know that the strong unstable is minimal in that case. And the second is that there is a unique U-Gibbs state. Okay, so this answers in a strong way the questions posed in that paper and also the ones previously posed by Bonucci, Diaz, and Urez for this particular family. Our third theorem is the following. It's a C1 open dense, but it holds for all partially hyperbolic diffeomorphisms in dimension 3. So for any three-manifold with a partially hyperbolic diffeomorphism, there's a C1 open and dense set such that any smooth diffeomorphism, so it has to be, the technology we're using kind of forces very high regularity, has a unique U-Gibbs state. So it's a very large class. And by the earlier stuff that Dima talked about 24 years ago, inside of this set of smooth, partially hyperbolic diffeomorphisms of three manifolds, even stronger dynamical properties hold. So I kind of alluded this earlier, but this uniqueness of U-Gibbs states has very strong dynamical implications. Okay, so I'm going to try very quickly, I think I'll skip a bunch of slides, to tell you something about the ideas in the proofs. Believe it or not, we're still writing the first paper. Well, we're still writing both of these papers, even though we proved this a while ago. And the reason is that we're not just dealing with Anosov diffeomorphisms, we're dealing with partially hyperbolic diffeomorphisms. We're not just dealing with partially hyperbolic diffeomorphisms, we're dealing with partially hyperbolic laminations. And so a lot of technical things come into the original simple ideas in the proof. So I want to just give the simple ideas. So the first is the magic horseshoes that were used initially in the work of Bonatti Diaz, a variation on that. The second, and this is to get the density of minimality inside the Anosov with expanding center, one-dimensional center. The second is S-transversality, which is a new concept that implies openness of the minimality condition. And the third is what I call Raphael's trick. So let's try to do, okay. Let's do the blender-like perturbations, or the magic horseshoes. So here's what we construct. So you imagine you have a partially hyperbolic diffeomorphism that's a Anosov with a one-dimensional expanding center, like perturbations of the second example. By an arbitrarily, or not even by an arbitrarily small, given such a diffeomorphism, it doesn't have to be smooth in this case, we construct a blender, or magic horseshoe. Here are some boxes in the construction of this blender. There are three directions. There's a strong, unstable, the center, which is expanding, and the stable, just to orient you. So these little boxes are obtained by intersecting forward and backwards images of the big boxes. And the little boxes in this construction and the horseshoe itself serves as a cross-section, or at least its center manifold, its stable manifold, serves as a cross-section for laminations, or invariant laminations, actually. And this persists. I said perturbable, but what I mean is this horseshoe that we construct, this special horseshoe that we construct, persists under perturbations. Its properties persist. And using this, we are able to produce a precursor to minimality. So here's the picture of the WUU lamination, and it has to hit all of these boxes with some multiplicity. And so here's how we construct a perturbation so that every leaf of the strong unstable foliation meets this box. We start with an open set, a fixed open set, and we consider its backwards iterates. So I'm going to show that some backwards iterate of U intersects every leaf of the strong unstable. So to do so, I take a very large pre-iterate. And you can't quite see in this, there's some like skinny tubes, and there's even skinnier tubes in this picture. And I'll give details in a bit. And then we look at how a strong unstable foliation meets these boxes. It could miss the set f to the minus k minus n of U, but we move the boxes a little bit independently and to ensure that every leaf intersects U. Okay, so that blender, that's how we're going to use this blender. And I have 15 minutes. Okay, we're doing okay. So I'm going to actually draw a picture of how this works, because I think it's pretty cool. It's pretty simple how this perturbation works. I'm linearizing things so we don't worry about nonlinearity for now. So here's a cross-sectional slice. So I had this stable direction, and the pre-image of U stretches across the box pretty much. You can assume it's a union of the stable leaves. So I'm looking at a center unstable cross-section, and I'm iterating the horseshoe. I'm just showing how to iterate the horseshoe. So here is, after 2 to the m iterates, what the horseshoe might look like, where m equals 1. Okay? So these are boxes long in the unstable direction, but they've shrunk. Notice that because the vertical is strong unstable, it gets shrunk more than, so this is F inverse. I'm sorry. This is after iteration under F inverse. This direction shrinks more than this direction because of partial hyperbolicity. And so if I iterate by F inverse some more, I get multiplicity as well as skinnier and skinnier boxes. And so what a horseshoe looks like, or what a blender kind of resembles, is the following picture. And you can see how when I take these intersections, I will obtain a Cantor set, because these things get smaller and smaller. But you can sort of believe me when I say that any strong unstable will intersect one part of this Cantor set near the middle of this square. Right? That's the blender property. And so we construct this, and I won't talk about how we construct a blender with these properties, but I want to show you how you can perturb F to get that some preimage of U meets every unstable leaf. Okay, so here's this F to the minus K of U. It's actually very long in the stable direction, but I'm not showing that. And just imagine iterating it as well many, many times until it's on the same level as these teeny tiny boxes at a later generation. And here's a WUU leaf. We construct our blenders in such a way that in our 2 to the m small boxes, these are to be considered really small, in every leaf is going to meet every one of these really small boxes within each of the 2 to the m small boxes. Okay, I hope that's clear. So let's focus on just this leaf, and let's zoom in so we can see what's going on. So I'm going to make a CR small perturbation. This is why I iterate until these boxes get minuscule. The reason is my perturbation will be supported inside the 2 to the m level boxes, but it will move everything on this tiny level the same amount. I don't know why that didn't happen. What happened there? I was supposed to show you a CR small perturbation. It didn't happen. Okay, the CR perturbation just looks like this, okay? And so it's on the order of the size of the teeny boxes in a bigger small box. And so by making them as teeny as I want, I can make that CR small. So here's a more close-up picture of F to the minus whatever of U inside one of these teeny boxes. And I want to estimate the probability that this fixed leaf does not intersect this piece of U. So you imagine I'm in this bigger box, and this little teeny box and this little bit of U is getting moved just like this on the order of the size of the teeny box in this direction. So what's the probability I hit this little set, this U, or F to the minus whatever of U? Well, it's proportional to the density. If I look among all perturbations inside of this one box, and what's the density? Well, we're on a tiny scale, and so it might decay sort of exponentially, but at a very slow rate. So within an M box, the probability that a given leaf fails ever to intersect this F to the minus whatever of U is less than 1 minus the density among all perturbations that go left and right. And now you just back up. And remember, we chose this horseshoe so that for every leaf, in every M box, there's a tiny box that meets that leaf. And there are 2 to the M such boxes. So on the level of boxes, the probability of failure for a given leaf is this. And now we can arrange this by choosing our choosing our range a little more carefully. We can arrange this so that this probability holds not just for the leaf, but for everything in a small neighborhood of the leaf, an exponentially small neighborhood, based on the contraction in this direction. And since you can cover the whole box with gamma to the n of these, your final probability that there exists a leaf that doesn't meet this pre-image under these perturbations, these independent perturbations, is this. Okay, so it's some product of something that's going to zero or almost super exponentially fast with something that goes to infinity exponentially fast. And so this probability, as m, the size of the larger boxes goes, well, the generation goes to infinity, this probability of failure goes to 0. And that's how you find a perturbation. That means there exists independent perturbations that achieve your goal. And so this is how we obtain density. So we just showed for every open set, there's a perturbation so that we can meet that, the orbit of that open set by every unstable leaf. And so a bare argument gives that this minimality is CR generic. So it's part of our result. That's the density. Then to get openness, we use this property called S transversality. So let me describe this property in the simplest case. Let's assume for now that we're Anosov on T3, where the center is uniformly expanded and everything is dynamically coherent. So the center is integrable and tangent to a foliation, and the center plus the stable is also tangent to a foliation, and so on, the center unstable. In this case, here's how we define this property. We ask that for every x, if we trace out the strong unstable of x, maybe a long ways, we find a place where it appears to cross itself in a transverse way. And so the way to say this rigorously in this setting is to say that if I take a piece of center unstable manifold through some point on this WUX, and I project it along stable leaves of the stable foliation, I get some kind of curve. And at some point in the curve, there's a point that's above, measured in the center direction, above the original leaf. And at some other point, it's below. And so, of course, that means there's some point that crosses as well. Right there, I guess. Okay, so that's S transversality. What does S transversality give you? So it's a failure of joint integrability of the stable and unstable. The first is that that's an open property. Once it holds under perturbations. The second is, like in this particular setting, where we're in the Anosov setting, if you already know that the unstable is minimal, then it literally is the condition that the unstable and the stable not be jointly integrable. That's the same as S transversality. So remember that condition in example 1 that I said was highly non-generic. That condition of joint integrability, as long as that doesn't hold, you get S transversality, assuming that the unstable is already minimal. That doesn't seem like it's giving you much. Well, Even now, it might not seem that it gives you much, but S-transversality implies minimality. So what does this give you? What it gives you is that if you're in the generic situation where you know that the strong unstable is minimal from the first part, and S-transversality holds, then it's robust. So I go from density to open density. And it's a very typical thing, right? Because the only way it can fail to hold is if we have this joint integrability. So let's quickly do the proof of why S-transversality implies minimality. So I take any point x. So I'm cheating a tiny bit. What I am doing is I am conflating minimality, meaning every leaf is dense, with dynamical minimality, which means every leaf has a dense orbit. So forgive me, I'm going to just do this, and I'm not really going to explain. You can then conclude minimality, okay? So I'm going to freely iterate. Okay, so really robust minimality. So I take an arbitrary leaf, a point x. I find some point z nearby where I have this transversality property. And I can find as close as I want to z, a point that's, but not z, on this center manifold, a point that's on this later version of the leaf. It's also on the leaf, okay? So this I get from S-transversality. And then let's just cut down. So these are two pieces of the same leaf. Now I'm going to iterate this, and look what happens. That tiny distance grows to macro scale. And I can take a limit, because I can start with an arbitrarily small distance. I can go arbitrarily far in the past. I can do all these tricks. And I can find that through this particular leaf, there's a center manifold where the leaf crosses it twice. Okay? So that's already a weird condition. But, and by the way, there's a sort of uniform thickness that has to hold for this crossing. I can make that as small as I want as well. And now I can apply S-transversality again. And now I can find another point. So I probably should have drawn it with this distance up here, the one between the top and the middle, comparable or even the same as the distance from the point middle to the bottom. And I can make both of those distances incredibly small. And because I am at least C1 plus holder, I can iterate so that those distances remain comparable throughout the length of a fixed piece of unstable manifold. So you iterate some more, and you get 3 basically evenly spaced leaves on the same center manifold. And you induct on the number of points that you can connect in such an arrangement evenly spaced along a center manifold. And you can do things arbitrarily tiny, and you can blow up, and you can take limits. So this is evenly spaced. And you can keep going and then take a limit, and suddenly you have a disk that's tangent to the unstable direction, not the strong unstable, but the center unstable, which is the Anosov unstable. And there's a disk inside this leaf, or in the limit of this leaf. And so any F invariant WUU lamination contains a disk. And because we're in the Anosov setting, we know that the unstable manifold is minimal, and therefore, now that is my alarm, and therefore WUU is minimal. So this is a summary of how we prove the first theorem. The second theorem, I can't really say anything about the measure theory side of the proof, except that it uses work of Anosov Katz. But I can say a little bit about Raphael's, and also work of Potrier and Zhang and Eskin, in the wrong order. But I can say a word about Raphael's trick. which is now we're in the setting of a T3, and we have an Anosov diffeomorphism, and it has a partially hyperbolic splitting with an expanded center. So we suppose that this S transversality does not hold, and we're going to get a contradiction by showing S transversality holds. So maybe we didn't have to do this by a contradiction. Anyway, in the universal cover, the strong unstable foliation maybe looks like this. We want to prove S transversality because that will imply minimality. So we apply the lift of the conjugacy to the linear example. The universal cover of the torus is R3? Yes, we're on T3. This is theorem 2. This is about example 2. I'm probably pushing my luck. So you know what I'm going to do? I'm just going to show you pictures. No words. Well, okay, I'll say one word here. So over here on the right is the linear foliation, which is minimal for this strong unstable. And what I'm going to show is if S transversality doesn't hold, then I'm going to show that the image of this strong unstable foliation for the perturbation under this structural stability homeo, Franks-Manning conjugacy, is linear. And that's all I need to show, exercise, okay? And so all I need to actually show is that the image of every leaf is somewhere linear, just somewhere it contains a little segment. Because then under iteration and the properties of the foliation, the linear map, it will actually have to be linear. And it will have to be the unstable, strong unstable, the linear. Okay, so now just quiet, just pictures. So I've established that S transversality holds, assuming that the image of the strong unstable is not linear. So the limit, so this is a contradiction. And I think I'll just end here. I had some further questions, but I think it's a good place to stop.
Okay, thank you, Amie. Maybe a quick question? Someone?
In your proof, you explained that you need to use the Helder property to apply S transversality, but perhaps you used this many times before. For instance, to estimate the, in the blended construction, the probability is also important, or
No, we don't actually need smoothness
you only need
for the
you only
blender.
need the Helder property at the very end of the proof?
Very end is the only place we use the holder property, yeah.
Okay, thank you.
Yeah. So for S transversality, for the openness and this, yeah, not used for the blenders.
In the results about the openness of S transversality, you have C1. Is it also, do you know if it's also true for C2 and higher regularities, or is there some technical issue there?
So if something is, so C1 openness is the best kind of openness because it means that if I take anything C1 close, the property holds. So in particular, if you take something C2 close, the property will also hold.
Oh, I see.
Yeah, so whenever I say C1 open, yeah, C1 dense, yeah.
Okay, thank you. Anybody else? Then thanks, Amie, again.